Hello, today we're going to be looking at time of flight mass spectrometry. So our checklist, we should be able to describe the main stages of a time of flight mass spectrometer, calculate the relative atomic masses from time of flight mass spectrometry data, and perform calculations involving kinetic energy and velocity. So let's dive right in. So overview. So there are four main stages in a mass spectrometer. The first main stage is ionization, the second main stage is the electric field, the third main stage is the drift region or the flight tube, and the fourth main stage is the detector. So we're going to look at each of these in turn and explain what's going on. Okay, so the first stage is ionization, and there are two ways that we can ionize a sample. The first one is what we call electron impact. So this means a beam of high energy electrons is fired at the gaseous sample and this knocks off an electron. Okay, so the sample is bombarded with high energy electrons from an electron gun, and this knocks off an electron to form a 1+ ion X+. The equation that would represent that is the sample needs to be gas, and it forms X+ gas plus E-. The second way a sample can be ionized is through electrospray ionization. This involves the sample first of all being dissolved in a volatile solvent and then put into a hypodermic needle. This gives a fine mist, so it's sprayed out, which is where the term electrospray comes from. The hypodermic needle is attached to a positive terminal of a high voltage power supply, and as the sample leaves the hypodermic needle, they gain a proton, and they gain that proton from the solvent. Okay, so let's look at the summary of this. To summarize this, the sample is dissolved in a volatile solvent. That's the first key point. It's injected through a needle to give a fine mist. That's the second key point. The needle is attached to a positive terminal of a high voltage power supply. That's the third key point, where each particle gains a proton from the solvent to form a 1+ ion. The ion this time has now got a proton attached to it. So the equation that would represent that is the sample, X in the gaseous state, is added to a proton again, and this forms XH plus G. Okay, so that would be the equation that we would need to give. As this is now positive, it can go through the rest of the time of flight mass spectrometer. Stage 2 of the time of flight mass spectrometer. So the first stage is they're ionized, so we've now got 1+ ions, either XH plus or X plus. The second stage is an electric field. An electric field will accelerate the ions so that they have the same kinetic energy. Okay, so that's the key bit there. So the ions are accelerated by an electric field to the same kinetic energy. So all ions leaving the acceleration area will have the same kinetic energy, where they go into the third region, which we call the drift region or the flight tube. So these ions will now all have the same kinetic energy as they leave here. Because they all have the same kinetic energy, they will travel at different speeds depending on their mass, as this is a mass spectrometer. So the heavier ions will take longer to hit the detector than the lighter ions. So that is how it separates the sample. So this drift region is the same distance, it's the same length, so each ion will take a different amount of time depending on how heavy they are. So the positive ions leave the acceleration chamber with the same kinetic energy, they travel to the detector, the lighter ions will travel faster than the heavier ions. Those are the key points there. So stage 4 is detection. The detector is a negatively charged plate. As the positive ions hit the detector, an electron moves from the negatively charged plate onto the positive ion. This generates a small current. The current is proportional to the abundance of the ions present. So to summarise, the positive ions hit the detector, which is a negatively charged plate. An electron moves onto the positive ion, creates a current, and that current is proportional to the abundance. So, what do we get when we've done a mass spectrometer? We'll get data that looks a little bit like this. So we have the mass to charge ratio along the bottom, and we've got the relative abundance up the side. So this one has 79% of a mass of 24, 10% is a mass of 25, and 11% is a mass of 26. So the mass to charge ratio is essentially the isotopic mass, so it's the mass of that isotope. What I will say, and it's quite common to get an exam question like this, where it might ask you, for example, to explain a peak at 12 in a spectrum like this. So the biggest peak here, so the most abundant isotope, has a mass of 24. Because that is the mass divided by the charge, the mass to charge ratio, if the charge is +2 instead of +1, it will give a peak at 12. So a peak that's half of the most abundant isotope will usually be due to the fact that it has a charge of +2, so it will be caused by a +2 ion. Do watch out for that, they do ask that question quite a lot. So, how do we calculate the relative atomic mass from the data that we get? So we can use this equation. So the relative atomic mass is equal to the sum of, so this means sum of, it's equal to the sum of the abundance times the mass to charge ratio, which will usually just be the mass, divided by the sum of abundance. If the abundance is given in percentages, it's probably safe to assume that that will be 100%, but do just double check it just in case it isn't. Okay, so let's have a look at an example calculation. So we're going to try and calculate the relative atomic mass from the data that we just looked at. So the first thing we need to do is work out the sum of the relative abundance times the mass to charge ratio. Okay, so that is equal to, so we've got the 79, which is the relative abundance of the first isotope, times 24, which is the mass to charge. We're going to add that to 10 times 25, and we're going to add that to 11 times 26. Add all of that up, do that in your calculator, and you'll get 2432. We then need to divide this number by the sum of the relative abundances. So the relative abundance is 79.0 plus 10.0 plus 11, which equals 100. So we need to do 2432 divided by 100, which is equal to 24.32. So our relative atomic mass, which we need to think about how many significant figures to give it to, or how many decimal places, all of the data for the mass to charge has one decimal place. So in this instance, it's appropriate to give our answer to one decimal place, which is 24.3. You'll also notice on your periodic tables, all of the relative atomic masses are given to one decimal place, so that is definitely appropriate. So that is the answer, 24.3, and this is magnesium. So let's have a look at some exam questions now. So this is a little bit of a harder question. Okay, so we're told that a sample of sulfur consists of 3 isotopes, has a relative atomic mass of 32.16. The following table gives the relative abundance of 2 of these isotopes. So the first thing we need to realise is that there are 3 isotopes in total, and that the relative atomic mass is 32.16. Use this information to determine the relative abundance and hence the mass number of the third isotope. So we're being asked to do 2 things. 1, determine the relative abundance, and 2, determine the mass number of this third isotope. So we should, Because the relative abundance is in percentages, the total relative abundance should be 100%. So that's the total relative abundance, and that will be equal to 91.0 plus 1.8 plus x. We don't know what x is, that's the relative abundance. So to solve for x, we're going to do 100 minus 91.0 minus 1.8, and that will give us the relative abundance of the third isotope, which is 7.2%. So that's the first bit there that we've done. The second bit is to calculate the mass number of the isotope. So we know our equation is the sum of the relative abundances divided by, the sum of the relative abundance times the mass number divided by the sum of the relative abundance. So this time we know that the answer is 32.16. We know that the relative atomic mass is 32.16. So that's going to equal the sum of the relative abundance, which in this first example is 91.0, times the mass to charge, which is 32 for this one here. We're going to add that to 33 times 1.8, and we're going to add that to that we don't know, so we're going to call this x again, and that is times 7.2, because we just worked that out up here. Okie dokie. Second stage of this is to, we'll expand the brackets and we'll rearrange. Oh, sorry, that's divided by 100. So I'm just going to move that up. So we're going to, first of all, I'm going to times this up by 100, and then I'm going to expand what's in the brackets here. So 3216 is equal to 2912 plus 59.4 plus 7.2x. Okay, so we want to find x, so we're going to need to rearrange this. Because these are all added, we can take them away. So 3216, take away 2912, take away 59.4 equals 7.2x. We do work this out, 3216 minus 2912 minus 59.4, and we get 244.6 equals 7.2x. So to get x, we just need to divide 244.6 by 7.2, which will give us 33.97. Okay. What would be an appropriate number of significant figures to give our answer to? Because that's the final part of the question. Give to an appropriate number of significant figures. So if we just scroll down, or up rather, just to look at the question again. So the mass number of the isotopes given up here, they're all to 2 significant figures. There's no decimal places, so it would be appropriate to give our answer to 2 significant figures, which is 34. So the final answer is 34. As you can see, that's 4 marks. So where you're getting the marks for here, you're getting 1 mark for working out the relative abundance. You're getting 1 mark for substituting things into the equation. You're getting a 3rd mark for getting 33.97, and the 4th mark is for an appropriate number of significant figures, which in this case is 2. Okay, let's have a look at another exam question. So this is an even harder exam question. So this time we've been told that 25 magnesium makes up 10% of this sample of magnesium, and we're told it's 24.3. There is some further information that we need to know as well, and that is that magnesium has 3 isotopes, 24 magnesium and 26 magnesium. This was actually given at the stem of the question, so that's at the very top of the question, but I just took out the little bit of the question here that we're going to look at. Okay, so use this information to deduce the percentages of the other 2 magnesium isotopes. So we know, let's look at what we know. We know the relative atomic mass of magnesium is 24.3. We know that 25 magnesium is 10%. So therefore we can deduce that 20, whoops, just rub that out. We can deduce that 24 magnesium plus 26 magnesium must equal 90%, because the total abundances must equal 100%. So because of that, we could use X and Y, but that will confuse things a little bit. So what we can do is we can say that the 26 magnesium is going to be equal to X, and we can say that the 24 magnesium is going to be equal to 0.9 minus X. Okay, so in other words, I've converted that percentage into a decimal, because that'll just make it easier. So this magnesium would be 0.1. And then the second thing I've done is I've said, well, if 90% is equal to 24 and 26 percentages, then if I say the 26 is equal to a number, which I've said is X, then the 24 magnesium is going to be equal to the 0.9, which is the 90% here, minus whatever this number is. So let's say, for example, X is equal to 5%, then this one would be 85%, because the 10% plus 5 plus 85 would equal 100. Does that make sense? Okay, so then we look at the rest of the question. So we know we're trying to get 24.3 being the relative atomic mass. We know that the 25 magnesium has a relative abundance of 10%, which I'm going to put as 0.1, just so I don't have to divide by 100. You could divide by 100 if you wanted to. Plus, and I'm going to use the 26 magnesium, which we said was equal to X, plus we've got the 24 magnesium, which we're going to say is equal to 0.9 minus X. Okay, now I'm going to expand the brackets. So 24, well, not expand the brackets, rather solve what's in the brackets first. So 25 times 0.1 is equal to 2.5. That's the rubber. 2.5. 26 times X is equal to 26X. And 24 times 0.9 minus X, this does need expanding. So I'm going to times the 24 by 0.9, and I'm going to times the 24 by minus X. So 24 times 0.9 is equal to 21.6, and 24 times minus X is equal to minus 24X, and we know that that equals 24.3. So let's now deal with the rest of this equation. So the numbers, I'm going to move over to the left hand side and I'm going to subtract them because they're positive, and the x's I'm going to combine and I'm going to keep those on the right hand side. So I'm going to do 24.3 minus 2.5, whoops, minus 21.6. So I've got all my numbers together on the left, and then I'm going to leave my x's on the right. So 26x minus 24x. Now I'm going to work out what that means. So 24.3 minus 2.5 minus 21.6 is equal to 0.2, and 26 minus 24 is equal to 2x. So if 2x is equal to 0.2, I can conclude that 1x is equal to 0.1, i.e. 0.2 divided by 2. So 0.1 is x. So therefore, the 26 magnesium is 0.1, which is 10%, and the 24 magnesium is equal to the 0.9 minus x, which is 80%. Okay, so that is 0.1, which I've then converted into a percentage, and this is 0.9 minus x, which is 0.8, which I've then converted into a percentage. So the final answer is here. Okay, third thing we said we would look at today is calculations involving velocity and kinetic energy. Okay, let's have a look at this question. In a time of flight mass spectrometer, ions are accelerated to the same kinetic energy. We're given the equation Ke equals 1/2 mv squared and V equals d over T. In the time of flight mass spectrometer, each 25 mg plus ion is accelerated to a kinetic energy of 4.52 times 10 to the minus 16 joules, and the time of flight is 1.44 times 10 to the minus 5 seconds. Calculate the distance travelled in meters in the time of flight region. So, the first thing I think we should do is look at the information that we've got from the question and write this down. So we were told here the kinetic energy is 4.52 times 10 to the minus 16 joules. We were also told the time of flight, which is t, is 1.44 times 10 to the minus 15 seconds. We also know that it's a 25 mg plus isotope. So we know that 25 grams of this substance is 1 mole because it's 25. So if we divide 25 grams by Avogadro's number, that will tell us the mass of 1 mg plus ion, which is 4.151 times 10 to the minus 23 grams. Okay, so that because Avogadro's number tells us the number of particles in 1 mole. We know that the mass number here is the mass of 1 mole in grams, because the mass of anything, the relative atomic mass or the mass number of anything, is the mass in grams. So we get told that. So we can write this here. However, this is something that's really important. The mass is in kilograms in this equation, and we've just calculated the mass in grams. So we need to divide this by 1,000 to get the mass in kilograms. So that would be 4.151 times 10 to the minus 26 kilograms. Okay, so now we've extracted that information, we can have a look at the two equations. There are several ways you could do this, but the way I'm going to show you involves combining the two equations. So we've got kinetic energy is equal to 1/2 mv squared, and we know that velocity is equal to distance over time. So what I'm going to do is I'm going to substitute in for the v here d over t. Okay, because the v appears here and the v appears here, I'm going to merge the two equations together to come up with a new one, which is Ke equals 1/2 m d squared over t squared. Okay, now I can take the information that I've got up here and I can put it into my equation. I can rearrange the equation to get it in terms of d, and then I can solve. So let's get on with rearranging the equation first. So all the numbers on the bottom, so the 2 and the t squared on the bottom, I'm going to multiply up and put them up here. So I'm going to end up with 2ke over 2ke t squared equals m d squared. Okay, now I just need to divide both sides by the mass, so I'm going to rearrange this again, which will give us d equals 2ke t squared over m, and that's d squared. Obviously, if I want to find out d, I'm just going to need to rearrange, square root that. Okay, so let's put those numbers in. So as we calculated, or as we extracted from the question earlier, we know that 2 times 4.52 times 10 to the minus 16, because that's the kinetic energy, times t squared, which is 1.44 times 10 to the minus 15, divided by the mass, which we calculated earlier, which is 4.151 times 10 to the minus 26. That all equals d squared, so if I square root that, that will give me d. If you put that into your calculator, you should get an answer of 2.13 meters. Okay, let's have a look at this next and last exam question for today. So this came up in the 2018 A-level paper, not the AS paper. So the 79 Br plus ions took 6.69 times 10 to the minus 4 seconds to travel through the flight tube. There's two parts that they're asking us to do. One is to calculate the mass in kilograms of one ion of the 79 Br plus, and two, calculate the time taken of the 81 Br plus to travel through the same flight tube. And then we're given some information that we'll need to use. So step one is to calculate the mass in kilograms. We do that exactly as we did in the previous one. That is, we know that 79 grams of 79 Br plus is 1 mole. So we only want to work out the mass of one atom, so we need to divide it by Avogadro's number, but also look at the question. We're being asked to give our answer in kilograms. So we need to do 79 divided by 1000, which will get our answer into kilograms, divided by Avogadro's number, which is 6.02 times 10 to the 23, which we're given here. And that will give us the mass in kilograms of one isotope, which is 1.31 times 10 to the minus 25 kilograms. Okay, so that's part one done. Step two is to calculate the time taken for the 81 Br plus ion. So we know the time of the 79 Br plus is equal to 6.69 times 10 to the minus 4. And we've got these two equations here that we're going to use. So how do we go about doing that? Well, the first thing we need to appreciate is that the kinetic energy of the 79 Br plus ion is going to be equal to the kinetic energy of the 81 Br plus ion. The reason for that is when they leave the acceleration chamber, they're accelerated so that they have the same kinetic energy. We can then substitute in to that equation half mv squared, and we can pop in the d over t, because we know kinetic energy is a half mv squared, and we know that velocity is d over t. So we're just going to substitute the d over t into the v there. The other thing that we're going to do is the mass, we know from calculating up here, is 79 divided by 1000 over Avogadro's number. So the mass is the mass of the isotope divided by 1000 divided by Avogadro's number. So I'm going to write all of that out here. So a half of 79 over 1000 divided by Avogadro's number times by d squared over t squared for the 79 isotope is equal to a half times 81 divided by 1000 over Avogadro's number times d squared over t squared 81. Now you'll notice for the d's I didn't actually write out the 79 and the 81 here. I didn't write out the 79 and the 81 there because the distance is the same, because it's the same flight tube. Okay, so the next thing I'm going to do is I'm going to cancel out like terms. I'm going to simplify this equation down. So anything that appears on both sides of the equation I can cancel. So I've got a half, didn't mean to delete that, but I have, and a half there, so I'm going to cancel those out. The Avogadro's number is on both sides, 1000 is on both sides, and the distance is on both sides. So I've really cancelled down quite a lot of this equation. And that's going to leave us with 79 over t squared for 79 is equal to 81 over t squared for 81. Now we know the time. We know the time for this one. It's 6.69 times 10 to the minus 4, because that's the time given up in the question, all the way up here. So now we only have one thing left to find. So 79 divided by 6.69 times 10 to the minus 4 squared is equal to 81 divided by t squared. Rearrange that equation, so I get t equals the square root of 81 over 79 times by 6.69 times 10 to the minus 4 squared, square root the whole of that, and that will give me my answer, which is 6.77 times 10 to the minus 4 seconds. So to summarise what we've looked at today, we've looked at describing the main stages of a time-of-flight mass spectrometer. We've looked at calculating the relative atomic masses from time-of-flight mass spectrometry data, and we've looked at calculations involving kinetic energy and velocity. I hope that video helped. Please leave a comment if you've got any further questions you have, or if you've got any other suggestions for any other topics you'd like me to cover. Thank you again. Goodbye.